The next step is typically temporal filtering. Now, the idea with temporal filtering, if you think back to my description of the bold time series as made of signal plus sources of noise, then what this does is it tries to eliminate certain sources of noise. Look at the graph on the bottom right. Now, this is known as a power spectrum graph. If you've never seen one, on the x-axis, it has some form of either time or period or hertz, so the frequency of some event. And on the y-axis, it has the intensity of it. Now, what I'm showing here is the signal. So for example, in this imaginary task, the period of our task is exactly 30 seconds. So it turns on and off every 30 seconds. And this is what we want to see. And maybe there's some harmonic, something happening at a different periodicity. But for our purposes, this is the period of the task. So this is our signal. And everything else, you see this yellow line, that's noise. And so you can easily look at this and just take a visual signal in terms of its power to noise ratio. Which of the two will be bigger? Well, the noise. So our signal to noise ratio is not great. So temporal filtering helps us get rid of noise, helps us diminish the yellow and increase the green. Relatively speaking, increase the green. Now, you should keep in mind that there are two types of noise. There's white noise. White noise is defined as noise that is the same across all frequencies. White noise is pretty easy to counter. If you just do multiple trials, white noise is random. If you take multiple trials, it'll wash out. So no problem. The problem is when you have non-white noise. And an fMRI, which is this part of the spectrum right here. Now, this part of the spectrum, which is not white, typically depends on a lot of things that come from acquiring MRI data in our circumstance. For example, heartbeat. Heartbeat will often look like a slow frequency, powerful source of noise. Respiration will often look like a slow frequency type of noise. Learning is a slow frequency type of noise. Alertness, changes in alertness is a slow frequency type of noise. Now this noise, because it's so-called colored, meaning it's not the same across all frequencies, as you can see, it changes. It's more powerful at low frequencies, right? The low frequencies are on the left, high frequencies are on the right. So the colored noise has this, it's known as a 1/f profile, so 1 over the frequency profile. Really powerful at the low frequencies and then slowly decreases as you go towards higher frequencies. Now this noise we have to address. We have to somehow clean it. Let me give you a couple examples just to help you understand what I mean. So this is our voxel of interest, the voxel we described earlier. Now this is a pretty good looking voxel in terms of, if you look at it, you can kind of see the signal. It's pretty obvious to detect, right? But this is a clean signal. So the types of noise that you can have so this is the signal part. And now we will add noise to it. For example, one type of noise could be a very slow, see this drift? This is a very slow frequency noise. It's a slow drift in your signal. So if you added this type of noise to your data, it would look like this. And fMRI time series sometimes look exactly like this. You just kind of slowly climb, or maybe you have this slow frequency, and then your signal would look like this. And remember what we said? I can explain the ups and downs every 16 seconds in this task, because that was my, in this time series, that was my task. I can't explain why it slowly drifts up. That is low frequency noise. I can't explain why it goes a little up and a little down. That is low frequency noise. I gotta get rid of it. The magnitude of this slope, or the magnitude of this up and down, is just so much bigger. I mean, visually, you can see that it's so much bigger than the magnitude of my changes of interest. This one, this one, this one, this one. So if I did signal over noise here or here, the noise is just too big, right? The noise will drown out the signal. So these are examples of low frequency noise. You can also get high frequency noise, though it's much more rare in fMRI. So this is a form of very high frequency noise, something that changes much faster than my task. I should say, what counts as low frequency or high frequency? For our purposes, anything slower than my task, anything that changes slower than, every 16 seconds or 32 seconds, which is my task, that's low frequency. Anything that changes faster than my task that I can't explain, that's high frequency noise, okay? So I can explain stuff that changes at the periodicity of my task, which is 16 seconds on, 16 seconds off. So exactly 0.031 hertz. Stuff that changes at that periodicity, I know exactly what it is. It's my task. Anything that changes slower than that, I don't know. It's noise. Anything that changes faster than that, I don't know. It's noise. I can't explain it. All right? So if you took this signal and added this high frequency noise, it would look like this. See, now there's much more wiggling inside of my time series. And here again, the signal to noise ratio is not very favorable. Now, temporal filtering is a way to remove this too slow or too fast frequencies. Let me give you an example. Let's take this, this time course right here. If you were to take the power spectrum of it, if you were to decompose it in its power spectrum, it would look like this. What this is showing, again, it's showing hertz on the x-axis and power on the y-axis. Now, if you look at this, see this tiny bump right here? It's exactly at 0.031 hertz. Exactly the periodicity of my task. So this, what is this? That's my signal. This little thing here is the power of the ups and downs that happen during my signal. What is this gigantic, ginormous thing right here? That's noise. Anything else, any other wiggling, see this wiggling up here? That's all noise. So look at this power spectrum and tell me, how good is the signal to noise ratio? It sucks. Too little signal, too much noise. We got to do something about this. And for example, this is the periodicity of my task. So the noise, the bulk of the noise is below the periodicity of my task. So it's a low frequency noise. So in order to do that, in order to get rid of it, we're going to use a high pass filter, which means we're going to use a filter that allows high frequencies to pass and cuts off low frequencies, which is what we want to do here. The filter looks like this. You can think of it a bit like a knife. Anywhere it's up, you keep the data, keep, cut off. All right. So if you think of it in terms of our power spectrum, keep, cut off. So anything that changes that has a frequency above this line, we're keeping. Anything that has a frequency slower, we cut it. It's like a knife. You go in there, you go in the power spectrum and say, okay, I'm going to keep anything that moves at these frequencies and these frequencies and these frequencies and these frequencies. And once I get here, boom, I'm going to cut it off. So anything that is too slow to be my task, I'm getting rid of that. In other words, this big up and down, I'm going to cut it off because that's not my task. I don't know what it is, but it's certainly not my task. So let's remove that frequency. And so if you do that, what you recover is exactly our nice time series. And if you take the power spectrum of this, it looks much nicer. This is my task. Everything else is noise. See, there still is some noise around. I didn't get rid of everything. I only got rid of the very low one. But still, now that the difference in magnitude between my task, the relative difference between my task and all the noise, anything that is not my task, is very favorable. So now, by cutting off this giant noise, I managed to increase by a lot my signal to noise ratio. Again, visually, the signal to noise ratio was very unfavorable. Here, now that I got rid of that slow frequency noise, it's much more favorable. Signal, that's the power of my signal, And this is the power of everything else. Good signal-to-noise ratio. Just to give you another example, but in an event-related design. So this is an event-related design. So it's harder in here to see where the task is because it has a jittered timing. The power spectrum looks like this. It's tough to say, but my signal is actually somewhere in here. See everything else? All this wiggling? That's too fast to be my task. It's not my task. See these two giant mountains right here? Not my task. So this is low frequency noise, and everything above is high frequency noise. So we're going to use a high pass filter, the same as before. We're going to keep anything that is higher, that is high, and then we're going to chop off anything that is low. If we do that, here's what we get. And it's hard to tell the difference visually because it's an event-related design. But if you take the power spectrum of this, it looks much better. Here's my task, and that's noise. So again, using the high-pass filter, we've recovered a lot of signal compared to noise, or rather, the relationship of signal to noise is much more favorable. Of course, you can get the opposite problem. If you have too much high-frequency noise, and sometimes, I should say, low-frequency noise sources sometimes get aliased to high frequency. So sometimes heartbeat or respiration that might be pretty slow sometimes appear like high-frequency noise, just because they get aliased into higher frequencies. So if you were to take the power spectrum of this, what you would see is this. Now, this is my task, as usual. That's noise, right? And what type of noise is it? It's a high frequency noise because it's higher than my task. So to get rid of high frequency noise, we're going to use low pass filters. So it's the exact reverse of the high pass filter. We're going to keep anything that is low, and then we're going to chop off anything that is high. Right? So you can imagine putting it here. We're going to do whoop. Anything that is low, we're going to keep, and then anything that is above a certain frequency, we're going to get rid of it. And so now we're back to having our nice up and down signal because we removed these too fast oscillations. If you take the power spectrum of this, boom, there we go. Signal to noise, much better than before. So these two strategies of the high and low pass filtering are ways to get rid of stuff that is either too fast or too slow to be my task of interest. Again, what we're doing is we're getting rid of noise so that we can maximize the signal to noise ratio. I should say, in your conventional fMRI, we typically do high pass filtering. We usually do not do low pass filtering. So how do we actually implement high pass filters in fMRI? Well, there are two main strategies. SPM, for example, used to, I'm not entirely sure, I think they still do, I'm just not sure if the latest version does. But SPM includes in your statistical model a number of regressors using a cosine transform basis set, which is what you're seeing right here, which are meant to just soak up variance. Essentially, it's additional regressors in the X matrix that are meant to model any drifts. Just to give you an example, this purple one right here would capture anything that would slowly drift. So any kind of slow drift going up or going down, anything that moves in that way would be regressed out by this regressor right here. Anything that had kind of a slow up and down or down and up would be removed by the cyan regressor. Anything that had a quadratic form would be removed by this orange one, and so on and so forth. So SPM, if you think of your X matrix, so this is the time series of a voxel, this is your X matrix, so the first regressor is the task, on, off, on, off, on, off, on, off. SPM just automatically adds a number of regressors here meant to capture these slow drifts. And it will put in as many regressors as it needs to model whatever high-pass filter you selected. Now, FSL uses a completely opposite approach, and we will see this over and over again. SPM and FSL are just philosophically different. SPM likes having sort of these theory-driven, ex ante expectations on how to address stuff. So for example, sure, in this case, there are slow frequencies, we're going to model them. And these are the type of shapes of slow frequencies that you might get. Let's include them in the GLM. FSL instead, philosophically completely different. They like data-driven approaches. So what FSL will do in order to remove slow drifts, FSL will actually take each voxel and the time series of each voxel, which is what you're seeing here in yellow, and it will fit a Gaussian weighted running line. In other words, it will take a Gaussian and it will convolve it at every time point with the voxel time series. In other words, it'll kind of smooth out the time series and the convolution over time. So take this Gaussian and slowly move it over the whole time series. What you will end up with is the convolution of the time series and the Gaussian, which is this purple line right here. So FSL goes inside the data and says, okay, let me see what slow drifts are there in there. And your slow drift is this thing right here. So FSL, instead of saying, okay, let's model it, FSL likes going in the data and then removing whatever is inside the data that you don't like or that you don't need. So the first step is go in the data, fit a Gaussian weighted running line and derive this slow trend. And then you subtract the slow trend from the time series. And so this is showing you in red, it's the original time series. You kind of see it under. In green is the time series after the high-pass filter has been applied. In other words, if you can see what happened here, you can best see it towards the end of the time series. This whole section of the time series here, FSL noticed that there was some kind of slow drift up, so it kind of pulled down the whole time series in that region. So SPM models it. FSL goes in the data and say, let me see what are the slow drifts in here, and then I'll just remove them.